To calculate the value of Tajima's D. This is the sequence we are going to use, and this is the number of individuals that we'll be using. Here we have 5 individuals, and here we have the number of polymorphic sites. So in this example, we are going to use the first individual as our reference. So what we have to do is compare individual number 2, 3, 4, and 5 to this reference. So basically, we just have to look at the sequence of these individuals to see if they are the same with the reference. And if they are different, we need basically to determine the nucleotides that are different. And those nucleotides, when we add up together, they will give us the number of polymorphic sites. So by looking at the second individual, we can see that the sequences, they are not the same with the reference. Comparing this sequence and this one, we can see the only difference is that here in the reference we have A, nucleotide A, and in the second individual we have G. In this sequence, we can see here we have C and G, so these are different. This sequence and this, they are the same. This sequence and this, they are different because the difference is here we have G and C. So the number of polymorphic sites that we obtain in the second individual is 3. We obtained one here, another one here, and another one here. So pretty much we have to do the same with the third individual. Compare this individual to this. And the number of polymorphic sites is 2. Similar, we do the same to the individual 4 and 5. We compare them to the reference. And the number of polymorphic sites obtained is 2 with the 4th individual and the 3 with the 5th individual. In total, in this example, there is 10 polymorphic sites. So we obtain 10 nucleotides that are different to the reference. Let's see if we use the second individual as a reference. We do the same as we did before. We compare the third individual to the second, 4th individual to the second, compare the 5th individual again to the second. Just by we look at the sequences to see if they are the same or different. So we can see here, this sequence and this is different, and it's only different by 1 nucleotide. So the number of polymorphic sites is 1. This sequence on the 4th individual, it's not the same with our reference. We can see it is different with 2 nucleotide sequences here and this one. Here there is C and G. Here we have AA. Again, here there is a G, but here we have C. This sequence and this, they are the same. This sequence and this one again, they are the same. So the number of polymorphic sites on the 4th individual is 3. With the 5th individual, the number of polymorphic sites obtained, we can see is 2. So in this example again, the total number of polymorphic sites obtained is 6. Let's move on, use the third individual as a reference. We compare the 4th to the 3rd, the 5th to the 3rd again. The number of polymorphic sites we can see that is 2. These are these nucleotides that are different to this sequence. So the total number we can see, we only have 3 in this example. What if we compare the 4th individual? We use it as a reference. So we compare this 4th individual with the 5th. We can see that the nucleotide sequences, they are pretty much the same, except here, instead of having a C, we have G. So the number of polymorphic sites in this example, we have 1. So how can we find Tajima's D? We know to find Tajima's D, there's 2 measures of nucleotide diversity. One is the number of polymorphic mutations. These are the average number or pi. That's the average number or polymorphic mutation. It is the sum total from previous tables. divided by the number of comparison. So we know that in our first individual, we had 10 as the total number of polymorphic sites. In the second example, we found 6. In the third example, we found 3. In the fourth, we found 1. So let me just remind you those ones. Those are these numbers: 10, 6, 3, and 1. So mainly to find those numbers, all you have to do is use the first individual as a reference. You compare the second to the first, third to the first, fourth to the first, and fifth to the first. Then you move on and make the second individual as a reference. So then you compare third to the second, fourth to the second, fifth to the second, and so on. So these are the totals from previous table. We add up them, then we divide by 10. This 10 is just denotes the total number of individual sequences that were compared to the reference. We know that in the first example, we used individual 1 as our reference. So we compared individual 1 to 4 individuals. 1 was compared to the second, 1 was compared to the third, 1 was compared to the fourth, and individual 1 was also compared to the fifth. So all the comparison we made from all the examples we did, in total they are all 10. So to find the value of pi mainly, you just have to do sum totals from previous table divided by the number comparison. And the number comparison we had from all the examples is 10. So the pi here, we have the value of pi is 2. So what this value tells us is that on average, if 2 chromosomes are taken blindly from the population, they will differ by 2 mutations. So let's see what theta tells us. Theta is the number of segregating mutations, or the number of polymorphic sites. This number is 4. You might be wondering, how did we find 4? So this was the first example we had. And if you look in this example, the number of polymorphic sites, we have to look to find theta. We just have to look in the sequence, the sequence where we obtained the polymorphic sites. So here we can see in this first column, the nucleotide are the same, A. In the second column, they are pretty much the same as well, GG. But in the third, we can see here there's difference. We have A. So this is our first polymorphic site. If you look in the fourth column, there's no difference. All the nucleotide sequence, they are the same. In the fifth column, we can see that there are difference. There's a difference. Here we have A. However, the second individual has G. So the number of polymorphic sites here we have is 2. 1 and 2. If you look here, another polymorphic site occurred here. These are the sites where there was differences was obtained in the nucleotide. So here we have our third polymorphic site, and here we have our fourth polymorphic site. So it doesn't matter if the nucleotide they are different, as long they all occurred in the same position. That's what matters. So here they all occurred in the third position. Here they all occurred in the fifth position. Again here, fifth position, fourth position. So the number of polymorphic sites is 4. 1, 2, 3, 4. So this is theta. So to find the Tajima's D, basically you just have to subtract the two numbers. So little d will equal pi minus theta, which is 2 minus 4. And this value is minus 2. So what we know that Tajima's D is denoted by capital D. So we have to divide it by the standard deviation. In this case, standard deviation is 1. However, in all the examples in molecular biology and genetics, when you calculate the number of Tajima's D, but the value of Tajima's D, the standard of deviation is always 1. So Tajima's D, meaning you can just say is pi minus theta, which is 2. So here we can see how we can learn how to interpret this value. We know we have got a negative value. So this value is just telling us that there is excess of raw frequency polymorphism. So this is constant with the idea of purifying selection, population expansion, or hitching. So in other words, we can say it is selective sweeping. If it was a positive value, then we will say we have excess of high frequency polymorphism. So in summary, to find Tajima's D value, all you have to do, you need to find these two numbers. These two measures, they are really important. You need to find the number of polymorphic mutation, which is pi, and the number of segregating mutation theta. Once you find those values, you can just take the difference between them, and that will give you the value of Tajima's D. Thank you very much for watching, and I will see you in the next video. Please don't forget to subscribe.